Pre-Calculus, Chapter 2, Section 6, Rational Functions and Their Graphs. And this is Part 2 of the notes. So let's continue where we left off. Let's look at some basic reciprocal functions. So f of x equals 1 over x, and f of x equals 1 over x squared. I just want you to take in the basic characteristics of these parent functions. So if we look at the graph on the left, this is an odd function. You can tell because of the graph being symmetrical about the origin. Also, if you plug in negative x for x, you get the opposite of the original function. So the original function is 1 over x, and you would get negative 1 over x. Also, notice that this has vertical asymptote at x equals 0 and a horizontal asymptote where y equals 0. So right on our axes. And then you'll have points in quadrants 1 and 3, and those points will create together the branches of this graph. Now look at the graph on the right. F of x equals 1 over x squared. Notice how it changes when the x is squared. We have an even function that is symmetrical about the y-axis, and if we plug in negative x, we still get the original f of x function. It has vertical and horizontal asymptotes at x equals 0 and y equals 0. And then you can see the 3 points in quadrant 1 and in quadrant 2, how those work together to create the branches that approach those asymptotes. So thinking about the parent function on the left, let's use transformations to graph our new g of x function in example 9. So g of x equals 1 over x plus 2 minus 1. So look at the graph that I have, and I graphed this on Desmos. This is the parent function. So notice it has our x and our y, our vertical and horizontal asymptotes right on the axes, and our branches, and I have identified 2 points, 1, 1, and negative 1, 1. Now looking at g of x, I can see I have an h value of negative 2 and a k value of negative 1. So that means my graph will shift 2 to the left and 1 down. So now look at my new Desmos graph here. I have shifted each of the points 2 left and 1 down. I can simply subtract 2 from each x coordinate and subtract 1 from each y coordinate. So now my new points are negative 1, 0 and negative 3, negative 2. My asymptotes shift as well. So my vertical asymptote has shifted 2 to the left at x equals negative 2 and 1 down and my horizontal has shifted 1 down where y equals negative 1. Nothing else has shifted, stretched, or shrunk, so my branches are the same as the parent. So that's one way that you can graph a rational function, if it's in this form where you can recognize the shift in the values. Sometimes, though, you'll not be able to recognize the shifts, so you can use a different strategy or process to graph a rational function. And here are 4 steps. So the first thing that I like to do is to identify the asymptotes. So the vertical asymptote by setting the denominator equal to 0 and solving, and the horizontal asymptote by using the rule that we learned in part 1 by comparing the degree of the numerator to the degree of the denominator. Then find the x and y intercepts, if there are any, by plugging in 0 for x and y. Plot at least 1 point between and beyond each x-intercept, and notice it's at least 1 point. Sometimes between these breaks in the graph, we will plug in 2 x values so we can get an idea of what the curve is doing. And then you're going to use the information that you know previously from this class and other math classes of what the shape of this function should look like when you go to draw the curves. So let's look at example 10, and let's graph f of x equals 3x minus 3 over x minus 2. Let's start with identifying those asymptotes. So I'm just going to shift my steps here because I like to do that first. So my x-intercept, my vertical asymptote, I'm going to set my denominator equal to 0 and solve, and that is x equal 2. Horizontal asymptote, I'm going to compare the degrees of the numerator and denominator. They are equal. So I'm going to then look at the coefficients. Sorry, I got a little mistake there. Of our variables, 3 over 1. So our horizontal asymptote will be where y equals 3. The y-intercept, let's plug in 0 for x. And so our y-intercept is at 0, 3/2, and the x-intercept, let's set the numerator equal to 0 and solve. So we have the point 1, 0. So now on this page, we're going to look at the points, plot some points and put them in a table. First of all, I'm going to capture what we know. There's our x-intercept. Here's our vertical asymptote, our y-intercept, and then horizontal asymptote at y equals 3. However, I'm focusing on my x values, and then in my table I'm going to place values in between those. So I have 0, 1, and 2 in order from least to greatest. So a value that is smaller than 0 is 1/2. Sorry, it's not, -1. And then a value that is between 0 and 1 is 1/2. And then between 1 and 2 is 3/2. And then two values that are greater than 2, I'm just going to stay with my halves. I'm going to go 5/2 and 3. Now I quickly have written those y values. I have plugged each of these x values into my equation here to get the y values. And now I have 5 points to graph. So let's start with sketching those asymptotes. That's good to do because then it gives you an idea of where your points fall and where the branches will be. So on which quadrant with respect to those asymptotes they'll be. So let's plot those points, -1, 2, 1/2, 1, and 3/2, -3. And then let's plot our points to the right of the vertical asymptote, and then you can draw your branches. And so this together creates the entire graph of our transformed rational function. Let's talk about slant asymptotes. So the graph of a rational function has a slant asymptote if the degree of the numerator is 1 more than the degree of the denominator. So if you remember when we were going through the rule in part 1 of horizontal asymptote, we said if the degree of the numerator was greater than, then there were no horizontal asymptotes. That may be an indication, however, that there are slant asymptotes. So just see if those degrees, if the numerator is 1 more than the degree of the denominator. So let's take a look at this rational function. You can see that the degree of the numerator is 2, the degree of the denominator is 1, so it is the numerator degree is 1 more than the denominator. Now to find this slant asymptote, we're going to go ahead and divide this function, and we're going to use synthetic division. So remember to do that, we're going to take our divisor, which is +2, and then pull off the coefficients of our numerator, bring down our numbers, multiply diagonally, and add vertically. And what we're left with is a function that is 1 degree less than the numerator. So if I plug in my variable, it is y equals 2x minus 1 plus my remainder of 5. But what I'm interested in here is this part of my results, and that is the equation of my slant asymptote, y equals 2x minus 1. In this screen, you can see that I have this function graphed for you, and I have the slant asymptote. So notice my vertical asymptote at x equals 2, and then the slant asymptote is this red line here. This graph does not have any horizontal asymptotes, just the vertical and then the slant asymptote. And then the curves are what are graphed in between these asymptotes. let's look at an application of rational functions. Example 12. A company is planning to manufacture wheelchairs that are light, fast, and beautiful. The fixed monthly cost will be $500,000, and it will cost $400 to produce each radically innovative chair. Let's write a cost function. So C equals that fixed cost of $500,000 plus $400 for each chair. So we'll say times X. Now, the average cost function just means the cost per chair. So we'll take the total cost function of $500,000 plus 400x, and then we'll divide that by the number of chairs. And now you can see that application of a rational function. So now let's say, what if we produce 1,000 chairs in a month? Let's plug in 1,000 for x. If we plug it into the average cost function, then that will tell us what our average cost per chair is if we can produce 1,000 per month. So $900 is the average cost per chair for producing 1,000 in a month. Let's take this a little further. So what will happen if we can produce 10,000 chairs in a month? So we still just have that fixed cost of $500,000. So if we're able to produce 10 times the amount of chairs, then you can imagine that the cost per chair will go down. So see, now if we can produce 10,000 in a month, the cost per chair is $450. And then finally, if somehow we can produce 100,000 chairs monthly, we can use this average cost function to see what this cost will be. Perhaps that $500,000 is rent or something, just a fixed cost that doesn't change no matter how many chairs we produce. So that reduces us to $405 average cost for producing 100,000 chairs per month. Let's do something else. Let's find the horizontal asymptote. So I'm going to rewrite the function here, and I'm going to rearrange it so you can compare the degrees. So if you see the degree of the numerator and denominator are the same, so I'm looking at my coefficient. So y equals 400. What does this horizontal asymptote represent? This would be the cost per wheelchair that the company can approach as more are produced. Because they have that fixed cost of $500,000 and then $400 per chair, so they will always have that amount, so it won't go less than 400, but the more chairs that they produce, then the closer they will get to the cost just being $400 per chair. All right, this concludes the notes for Chapter 2, Section 6, Rational Functions, their graphs, and applications.